In this example, I'm going to explain to you how to construct a confidence interval for the difference between two means when you have independent samples. So the assumptions for this procedure are that you have two populations, and from each population, you have a very good simple random sample, so a quality sample. Then you need them to be independent of each other, and you need each sample size to be large, which is bigger than 30 data points, or you have to know that the population is approximately normal. Given these assumptions, the procedure will be very similar to a one population procedure. We'll compute the point estimate. We will use the critical value method, which is with the t distribution, that's the student's t distribution. And then we will compute the standard error, multiplying it by the critical value to obtain the margin of error. With the margin of error, that will give us our confidence intervals. Let's look at this example. Watch your step. In a study comparing the battery lives of two types of wearable devices, 12 smartwatches and 14 step trackers were tested. Following are battery lives for each device measured in hours. If appropriate, construct a 95% confidence interval for the difference in average battery life. So this was a study, and we have these samples, we're told. Given that this is maybe like a homework problem, we can assume that from the study that these samples are simple random samples. Otherwise, if this were like a more detailed problem, we might want to investigate further. But given what we have, we can probably assume that they're simple random samples. Now, the two samples are independent of each other. The battery life for a smartwatch is completely separate than the battery life for a step tracker. So these are independent samples. Another clue for them being independent is that one sample is size 12 and the other sample is size 14. So they can be dependent if they are different sizes. And then finally, because the samples are small and we don't necessarily know if battery life is normally distributed, we want to look at the data itself and see if it looks like it's approximately normal. And if the data is approximately normal, then we can assume that it came from a population that is approximately normally distributed. I'm going to use technology. I'm going to use Desmos to compute these to check normality. So I already have the data in Desmos, and what I'm using is the table feature, and I've retitled the descriptors. So I have W for the data from the smartwatch and T for the data from the step trackers. So what we're going to do is we're going to check normality. The size of the data sets is small, so I'm going to use a dot plot for both of them. The command for that is just dot plot. And then I'll put in the names of the data sets. And I'll hit the plus sign because that'll automatically show me my data. Here's the data for the smartwatches. What we're really looking for, are there any strong outliers anywhere in the data? Double checking, our smallest value is in fact that 17, our largest value is in fact that 30, and the rest of the data looks to be grouped around the middle. And I would say there's no strong signs of outliers or skewness. So we can imagine that the smartwatch battery life is from a population that's approximately normal. And so now we're going to do the same thing for the tracker. Change this W to a T, and then here's the tracker data. It's a little bit more condensed in terms of its settings, right? We have a lot more repeat values. But similarly, we don't have any strong skewness to the left or to the right. Most of our data is centered around the middle. And I would again say that this data looks to be from a population that's approximately normal. So I don't think that we have any issue with proceeding with the methods of the chapter. All right, following the procedure, we will compute our sample means and we will find our point estimate. Since we are given this data, we have to compute the sample mean ourselves. I'm going to let smartwatches be my N1s, my subscript 1 sample. So N1 is equal to 12 and X bar 1 is equal to 22.8. Battery life of the step trackers will be my subscript 2 samples, so N2 equals 14, and X bar sub 2 is going to equal the 17.6. The point estimate is X bar for the first data set minus the X bar for the second data set. That's the difference between the two means, which is 5.2 hours. And now we're going to pull up the student T distribution and find the critical values. This is a 95% confidence interval. That means alpha is equal to 0.05. The degrees of freedom are equal to the smaller of the samples subtract 1. So that's going to be 11. We're going to have outer. We're looking for the bounds for 0.05. And here is what the distribution looks like for this data. And here is our critical value, 2.201. Now we're going to compute the standard error and margin of error. And we actually can just compute the variance. Let's write those down. All right, so given the values that we have, going back to this formula, I can do is we can compute the margin of error. So the standard error is the square roots of these two quotients added together. Variance of sample 1 divided by the sample size. Still within the square root, the second quotient is the variance of sample 2 divided by the sample size. Now what we'll do is multiply that by the critical value, and we'll have the margin of error. I'm going to label this M. And now we can take our point estimate, which was 5.2 hours, and find our confidence interval. And these are our possible answers. Now let's interpret what they mean. So this is what they mean. Remember, population 1 is the smartwatches, and then population 2 is the step trackers. And so what this tells us is that this difference is larger than 0. And so it means that the smartwatches mean running time for their battery, right? Their battery life is more than the step tracker's battery life. So we're 95% confident that this is the case because the battery life are on the positive end, which means that the population mean for population 1 is larger than the population mean for population 2. That is how you find the confidence interval for population mean independent samples.